All right, we'll talk about these examples here that we have. The first one should be undefined, and that is because the first little section here, when I take the dot product of u and v, that gives us a scalar. And when we have a scalar, we can't do the scalar dotted with a vector. It's a vector dot with a vector. So you can't dot product a scalar with a vector. The second one, what we have here, this dot product will give you a scalar. And then we have a scalar, just regular multiply here. There's no dot between. It's just regular multiply the vector. And you can do that, and that will result in a vector quantity. The third one, the u dot v, will result in a scalar. So we have a scalar, and then we're adding the magnitude of vector w. So the magnitude is a scalar as well. So we have a scalar adding to a scalar, it's going to result in a scalar, and that's clearly okay there. The last one here, we have the dot product, which results in a scalar, and to it we're adding a vector. And you can't add a scalar with a vector. You can add scalar and scalar, you can add vector and vector, but you can't add a scalar to a vector. So that's undefined. All right, a couple quick examples here of actually applying that dot product, and for whatever reason the font that I have, the dot really here should be a little bit bigger, but that's okay. This is asking you to find the dot product for the following. So remember our dot product, so oops, I hit the wrong button here. Let's fix that up. Oh dear. Let's do undo. Undo is a good button. Thank goodness for undo buttons. All right, so u dotted with v is, of course, the magnitude of u times the magnitude of v, or the magnitude of v times the magnitude of u, it doesn't matter, times the cos of the angle between them when they're joined tail to tail. So we're going to have 8 times 11 times the cosine of 55 degrees. So this is clearly a degree angle. We're going to put that in the calculator and just get our answer there. And my answer when I worked that out on my calculator was about 50.5 joules. If you want to talk about work. This doesn't actually have context to it, so I can leave that off. Again, dot product, u dot v, magnitude of u times the magnitude of v times the cosine of the angle. Now, do you notice this angle does not have a degree symbol? So if it doesn't have a degree symbol, it's implied to be radian measure, plus it has the pi, so that's a clue there. So make sure you switch your calculator into radian mode for this one. And when I put that into my calculator, I got a negative 42.4. And that makes sense. This is an angle of, an obtuse angle. 3/4 of the way to pi is 135 degrees equivalent. So you would have your vectors working against each other on that one. All right, let's look at these properties of the dot product. Things that are true here for working with the dot product. A is a scalar here. If it is multiplying the dot product, the A can multiply the U, and then you would dot it with the V. Or you could do the U dotted with A times V. So those are all equivalent. Those are properties that are true. Here, if you have a vector dotted with the sum of two vectors, you can think of this actually as the distributive property because of the plus sign here, as opposed to the one before. If you think of the one before as just multiply, 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 you only, like if you had 3 times x times y, you either would make that 3x times y, or you make that x times 3y. It's not going to be 3x times 3y. Okay, so it doesn't distribute through because it's multiplication. The second one, on the other hand, it does distribute through. You could do u dot v plus u dot w. Okay, so this is the distributive property happening here. So you could think of that as like x times y plus z. You would hop through the bracket there. You would have x times y plus x times z. Okay, so just make sure you understand the difference because you have the plus versus just multiplying in the previous example. The order you dot things in doesn't matter. It's commutative. You could go either way with that. The last one is an interesting example here. If you dot a vector with itself, you're just going to get the magnitude of that vector squared. And if you think about that, these have the same direction. So your theta would be 0. So therefore theta is equal to 0 degrees. So if you do u dot u, whoops, I put a v, u, that would just be the magnitude of u times the magnitude of u times the cosine of that angle between them, and the cosine of 0 degrees is just a 1. So you get the magnitude of u multiplying itself times 1. Okay, so that just ends up being the magnitude of u all squared. So these are properties we're going to use in a moment here. Now, if you look at your unit vectors, remember I is the vector that lies along the x-axis with a length or magnitude of 1. J is along the y-axis with a length of 1. K hat is on the z-axis with a length of 1. So if you do I hat dot I hat, you're going to end up, so we're using that property right, the last property up here, you're going to end up with 1 to the exponent, because the magnitude of I hat is just 1, so you're going to have a 1 times the cos of 0 degrees, you're just going to get a 1. Similarly for j hat dotted with j hat and k hat dotted with k hat. If we have I hat dotting with j hat, I hat is along the x-axis, j hat is along the y-axis, we know they meet at 90 degrees. So the cosine of 90 degrees is 0, so a 1 times a 1 times a 0 will give you 0. So those will be true for all of these because they are perpendicular vectors to each other. All right, and we did have a little summary of that before. Now let's put this into play with some examples here where we'll come up with how to find the dot product of our vectors that are in their algebraic form. One other thing I want to mention though before we move on to our next page is going back to this one right here. So this line actually, so this one. If I had vector u dotted with vector, actually let's make that a t. Undo. There we go. Let's go t, vector t dotted with vector, or sorry, added to vector u. And then we want to dot that with v plus w. Okay, so I'm just extending that particular property. Again, distributive property is going to work here. We would have t, vector t, being dotted with vector v, plus vector t being dotted with vector w, plus vector u being dotted with vector v, plus vector u dotted with vector w. That's supposed to be a w. So really it's that distributive property, but when we do that, we're dot producting them, if that's even a word. So that's going to come into play in this next example here. So here we're going to put into play a way to come up with what the dot product of algebraic vectors actually looks like. How do we actually calculate that? So to develop that, I'm going to use the unit vector notation of vectors, where my original vector was ABC and my other vector was DEF. So we'll walk through this, finding their dot product using the unit vectors here, because we've got lots of properties for unit vectors. So we're going to have A I hat plus B J hat plus C K hat, and that has to dot D I hat plus E J hat, ooh, that was messy, plus E J hat plus F K hat. Now we're going to use that property that we went over, the distributive property here, to multiply our vectors. So I'm going to take AI hat and multiply each one of these by, or dot each one of those by the AI hat. When you're dotting these, when you're multiplying through or dotting, the scalars, the A and the D, get multiplied together. So you'll have A times D, and then the vectors get dotted. I hat is going to dot I hat. So that's a property we have up above on the previous page there. And then A is going to multiply the E. So I did this one. Now we're working on this one. And then we have I hat dotting with J hat, and so on here. A multiplies the F. We're going to have I hat dotting with K hat, and so on. B is going to now, so the second one now is going to multiply all three here. So we're going to keep going with this. I'm going to actually put the video on pause to save some time and put my answer up. All right, so since I had three terms dotted with three terms, 3 times 3 is 9. I have 9 terms in my expanded form here, and now I want to simplify some things here. I noticed that I have I hat dotted with I hat. Because of our explanation earlier, we know that that is equal to 1, so it leaves us with A times D times 1, or A times D. And then we have I hat dotted with J hat. Well, those are perpendicular to each other, so that's a 0. So that disappears. Likewise, this is 0, that disappears. These dotted together would be 0, that disappears. And now I get a 1 again. J hat dotted with J hat is a 1. So now I have a plus BE here happening, BE. And then, continuing on, J hat dotted with K hat would be a 0. K dotted with I hat would be 0. K hat, J hat dotted together is 0. And then K hat dotted with K hat is a 1. So we'll have a plus CF here. So that is our quick way to get the dot product of our algebraic vectors. So if we look at the ABC as our U vector here, and our DEF, we're really taking first component multiplied by first component plus our second component multiplied by the second component plus the third component multiplied by the third component. That still will result in a scalar value. So it's also still just our scalar product. It should be, because dot product should be the same whether you're doing it with algebraic vectors or our geometric vectors. We should still get a scalar out of that. So we have our summary here. Dot product of algebraic vectors would be given by this little formula here. So let's do the dot product of these two vectors. Nice and quick. U dotted with V would equal first component times first component plus second component times second component plus third component times the third component. So we get a 10 minus 3 minus 28 minus 31 plus 10 would be minus 21 there. So a scalar value. Now what is the angle between U and V? Now because that dot product is negative, we know that that answer should be between 90 and 90 and 180 degrees. We also know that if we were to do the geometric dot product, that geometric dot product has to equal the algebraic dot product, because they would be the same for both. Dot product has to equal the algebraic dot product. All right, so let's talk about that. Our algebraic dot product ended up being negative 21. Our geometric dot product would be the magnitude of U times the magnitude of V times the cosine of the angle between them. And we need to solve for that angle between them. Now that means we probably know how to come up with the magnitude of vector U. Well, yeah, by golly we do. We know that that's going to be the square root of the components added together after they've been squared. So we take all those components, square them, and add them together. For the first one, that gives us the square root of 83 there. And then we do the same for vector V. We find its magnitude using that formula. So 2 squared plus negative 1 squared plus 4 squared. And that's going to give us the square root of 21. All right, so now we fill in what we have here. We're going to have the square root of 83 multiplying the square root of 21, multiplying the cosine of theta, and that equals negative 21. We're going to solve for cosine of theta by dividing both sides by the square root of 83 times the square root of 21. And then I'm going to put all that in my calculator in one sweep motion so that I don't have a rounding error there. And if you need to, make sure you switch back to degree mode here. I got an answer of about 120 degrees between those two vectors, which makes sense in terms of the prediction that we would have had to have an angle between 90 and 180 because our dot product was a negative value. So hopefully this is making sense for you. Let me know if you have any issues. Send me an email.